Atomic structure and periodicity. Okay. We know up at this point that atoms are made of protons and neutrons in the nucleus, and electrons on the outside. That's where the chemistry happens. But in order to understand why certain groups behave similarly, we need to know something about how the atoms are built in an electronic sense. So that's where we're headed. Atomic structure. Right. We get the information that we get from most chemical reactions and from anything in outer space except for the immediate. Let's see, we've gone as far as Pluto with spacecraft. Yeah. No. Yeah, the New Horizon spacecraft flew by. Don't you remember that? No? Anyway, most of the information we get about the universe comes to us by light, electromagnetic radiation. So we need to understand what light is and how to use it. Right? Everybody's been to fireworks and we love all the bright colors. Some colors are really easy to make, like oranges and yellows. Reds are a little more difficult. Blues are almost impossible. But they're done. Excuse me. Made one? I've made, probably. I've made colors with chemicals using an open flame. You know, that's similar. I've tried flame tests in a teaching lab, and they never work. I think you need a hotter flame than we have here. I used to do it for my for tours that came through my lab when I worked for the USDA. We had a device called an atomic absorption spectrophotometer. It had a flame in it, and acetylene compressed air flame. And we aspirated solutions through that, and then we shined light through it and measured the difference in intensity on either side, and we could determine how much of an element was in there. But that flame is hot enough. You can aspirate different chemicals through it and get different colors. Most of them were grade school kids, middle school kids, and they always liked their favorite was strontium. Strontium gave them a hot pink. Yeah. So we want to know, why do we get these different colors? It looks like barium makes a blue color. Why do we get these colors? And why do different chemicals give us the different colors? Right. For this particular discussion, we're interested in not complex chemicals, but elements. Why do the elements give us these colors? Sometimes they're different in solution than they are in the flame. And that's a topic for another day, because solution colors are usually based upon coordination chemistry. As when you put a metal in aqueous solution, it surrounds itself with a certain number of water molecules, and that changes its electronic structure and how it behaves as where light's concerned. When you put it in a flame, it's just that element, and there's nothing else with it. Then why? Well, that seems like similar question to the second one. We can see different colors in blood. Right? Is anybody here a phlebotomist? You know a phlebotomist? When you take blood, taking blood from a vein is pretty simple. It's pretty easy. Right? And it comes out really, it's kind of dark. Sometimes it's almost blue. But when you need blood gases, you have to take it from an artery. And they usually go right in here at the wrist. You have blood gases. Go in at the wrist and find an artery. When that blood comes out, it's bright red because there's oxygen attached to the iron in the hemoglobin. That alters the spectra, the color of the iron, versus non-oxygenated iron in hemoglobin. I did my master's research on in Louisiana on crawfish. We had producers down there that would take crawfish, they'd buy it from the fishermen, and then they'd boil them, and they'd have a crew, usually women, a crew of women sitting at a table, and they would peel them and just remove the tail meat. Well, the tail meat is only 15% of the total mass of the crawfish. You got 85% waste. So they were desperate. These processors were desperate to know, what do we do with the waste, before the EPA gets hold of us, because we can't just dump it in the bayou. So that was part of my project, was try to figure out what these colors were in the shell of the crawfish. Especially when you boil them, they turn bright red. And we were thinking about using those compounds that were in the shells, mixing them in with fish food, particularly salmon, because the salmon that's farm raised and doesn't have these colors in their diet come out white meat, and people won't buy it. It's got to be pink. Right? If they're naturally caught, they already have pink from their diet. So if we put these carotenoid pigments from the crawfish waste in their diet and let the farmers feed them that, then their meat will be pink because they deposit it in their flesh. Well, there's a picture of one of the main compounds. It's a big molecule, and the colors are still related to electronic transitions from higher to lower or lower to higher energy levels, right? Whether they're compounds like this or whether individual elements. Okay, so electromagnetic radiation is light, and we need to know something about it. We need to, mathematically speaking, actually, if these three characteristics are definitive for different colors of light, you need to know the wavelength. We know what a wavelength is, right? If you look at a wave like this, the wavelength is the distance between these two crests. Right? And we give it has a Greek letter associated with it. It's the Greek letter lambda, the small letter lambda. That's the wavelength. And it's just a distance. SI units would be meters. Okay. And we need to know frequency. Frequency is if I train my eyeball on this position right here, how many of these crests pass my eyeball in 1 second? Cycles per second is the way we express it. Since cycles is not a unit of measure, it's just an expression of what's happening. The actual unit of measure for frequency, and the Greek letter here is nu, like that. The unit of measure here is reciprocal seconds because it's in the denominator. We've also given it another name, hertz. So if you tune into a radio station, AM stations are kilohertz, right? 1,000 hertz would be the frequency, 7 times 1,000. FM stations are megahertz, so it'd be 1,000,000 times that value would be their frequency.
Per second?
I'm sorry?
Per second?
No, a hertz. Well, hertz means reciprocal seconds,
yeah.
Right? Cycles per second. Yeah, right. Mm-hmm. Yeah, hertz and reciprocal seconds, they're synonymous. Same. We're just trying to honor one of the pioneers. Right? I forget his first name. His last name is Hertz, obviously. And then the other value we need to know is speed of light. And we give it a small c. And in a vacuum, it has a fixed value. Speed of light in a vacuum is 2.9979 times 10 to the 8th meters per second. That's how fast light is. And what we're saying is that for this wave to get from here to there, it can go that far in 1 second. So it's really fast. Okay, then we can relate all of those values in this formula. Speed of light is our constant. And for air, it's really close to that. So we just assume it's that for air also. In more dense, optically dense objects like diamond, it would slow way down. Slow it quite a bit. But we're only talking about vacuum and air. And this is equal to the wavelength times the frequency. And if you check your units of measure here are meters. Units here is meters per second. And this one is reciprocal seconds. So there you go, meters per second, meters per second. So let's look at the units and we got them. That's how I check myself. Be sure I've got it right. Okay. And there's the artist representation. What you'll notice here is that from the formula or from the picture, as the wavelength gets smaller from top to bottom, you see there, as the wavelength gets smaller, the frequency gets bigger. More cycles per second if the wavelength is shorter. Okay. Anytime you have a variable times a variable, a product of two variables equal to a constant, you have an inverse relationship. So if one goes up, the other goes down. All right. So now we've characterized, well, we've defined our terms, put it that way. Then we have what we call a spectrum of light. And the way they've got it set up here, longer wavelengths are to the right. All right, so we're increasing wavelength to the right. That means what? Increasing frequency is to the left, because they're inverse. So the frequency down here would be increasing. Also, we're going to find out in a couple of slides that as the frequency increases, so does the energy of the light. So the higher the frequency or the shorter the wavelength, the higher the energy that's packed into that light. Okay, so we can only see a small sliver, the visible spectrum. That's not all there is. Longer wavelengths. This side, the longer wavelengths of the visible spectrum is going to be red. All right. And you remember memorizing the colors of the rainbow? Mm-hmm. So red, orange, yellow, green, blue, indigo, violet is on this end. Okay. So the longer wavelength is the red, shorter wavelength is the violet. The smaller frequency is the red, and the higher frequency is the violet. So on this side, we have infrared. Okay. Then we have microwaves. Then we have radio waves. Okay. Longer wavelengths, longer wavelengths. FM is going to be on this side, and AM's on this side, and I think shortwave is in the middle. As the frequency gets higher, or the wavelengths get shorter, on this side we have ultraviolet. Okay. Then we have X-rays. Right? Same thing that your dentist fires at you when he checks your teeth, or a broken bone, whatever. And then the most energetic of all are the gamma rays. And, did we?
It's an anatomy.
It was a different one.
It was my anatomy class. So it's
Okay.
probably the same thing, but you talk about different ones.
So we use, that's the small letter gamma for in the Greek. The gamma rays are extremely powerful. They pack a lot of energy.
That's the blue, like blue color, the big game. Violet, yeah.
Well, no, because that blue is expanded from the visible. You can't see these. You can't see any of those. You can't see any of these. Now, there's some animals that can see infrared or ultraviolet. That's about as far as they go. Gamma rays can be produced in nuclear transformations, like in an atom bomb or in a nuclear reactor. They can also be produced in astronomical events, hopefully very far away, and they're usually very directional. So if you pay attention to the media, you may occasionally hear of a gamma ray burst. The gamma ray bursts are extremely dangerous, even if they're thousands of light years away. But if they're directional, so if they're not aimed at us, that's good. Because if a gamma ray burst hits us head on, it will strip our atmosphere and leave us with nothing to breathe. It's that dangerous. Now we've had the gamma ray burst.
No, like gamma ray.
Any gamma rays? Well, you can in a nuclear reactor.
Oh,
right?
We wouldn't see them like that.
No.
Not seeing them.
Gamma ray bursts, yeah. They're directional, but they tend to spread with distance. So we've kind of caught a glancing blow of one or two, and scientists have been able to detect them. That's why we know they're there. But we've never been hit head on with one. Yeah, it
would be like, would it be a huge thing? Like if it was to happen, we would hit head on.
You wouldn't know it.
Okay, we wouldn't.
No, you wouldn't know it until all your air's gone. Yeah, it would be mercifully silent. I mean, I wouldn't. The probability of something like that happening is like in the trillions to one. Yeah.
Like would it kill like the environment stuff? That would
Yeah. If you don't have any air.
I mean, like that. It would kill you. Would it kill you directly, or would it just kill like?
It could. Yeah. Yeah. Well, gamma rays can damage your chromosomes.
Oh.
Yeah. So, right, these victims of Hiroshima and Nagasaki when we dropped the bomb, some of them didn't die right away. Radiation poisoning destroyed their cells, and they eventually died.
So, like, how big? Like, if one of them did burst, how large of an area does it affect?
Maybe, I don't know. Maybe the orbit of Mars. It'd be that wide, right? So the glancing blows that we've seen have been really off center of our entire solar system. We've just caught the very edges of it to see what's happening, right? You need sensitive instruments to pick that up.
Okay.
Yeah.
Like X-rays, you know how they wear like that lead over here? What is like that?
It's a shield.
Is it like
Lead is a very effective absorber of X-rays. They're not as dangerous as they used to be. Right, when you get your dental X-rays, because most dentists now use electronic imaging. In other words, they stick that thing in your mouth and it's got a wire on it. Yeah, and it takes an electronic image, and you need much, much, much less X-ray to get the picture than when you had film. Well, it damages chromosomes. Yeah. Yeah. You know what cancer is? It's runaway cell growth, right? The cells that are cancerous cells have lost the ability to control their own growth. so they just keep multiplying and growing, but without any controls, right? And that's what damaging the chromosomes will do. It turns the cell loose. It kills most of them, but all you need is one to get started, and it will take off. Okay. We also have a series of values for the wavelength, and this is in meters. It goes from 10 to the minus 12 meters down here up to 10 to the fourth meters up here, I think. So it's a very wide range. Now, you may see another unit of measure for wavelength that's often used is rather than, let's see, we're in the neighborhood of 4 times 10 to the minus 7th here, up to 7 times 10 to the minus 7th meters, wavelengths, or violet to red, this range. But we don't have to say minus, 4.75 times 10 to the minus 7. We use a different unit of measure, so we don't have to use the scientific notation. So what we do is we use a different unit of measure, and if you take this value and add 10 squared to it, I take 4, 10 squared would be that, wouldn't it? Okay. So in order to keep it balanced, if we added 10 squared to this one, we have to take away 10 squared here, 10 to the minus 2, right? That would be equal to 4, wouldn't it? Okay. But it's still times 10 to the minus 7. Okay. So if we combine these two, we get 10 to the minus 9. So 400 times 10 to the minus 9, and this is our new unit of measure. Instead of meters here, this is nanometers, or nm. So a nanometer is 10 to the minus 9th meters, or a billionth of a meter. And that way, we can say the wavelength of visible light runs from 400 to 700 nanometers. You'll see that more often than you will this one. The problem with that, I mean, it's easier to deal with at this level, but the problem with that is if you try to use it in a formula, like C equals lambda times nu, you got to convert it back to meters, because C is in meters per second. Right? So if you're given a problem where it's in nanometers and you got to use that formula, you got to change it back to meters first. And it's really simple. Remember my trick? Nanometers. If you got something out here, then times nanometers, this equals 10 to the minus 9, right? Times whatever this one is. Okay. I spent far too much time on that slide. I don't want to eat up all our lab time, though. All right, there is a relationship between light and energy, right? Light itself carries with it energy. You can also convert other forms of energy into light. In this case, the pickle is being electrified with direct current, right? And it's glowing. You got a glowing pickle. It probably smells too, because there's a lot of extra heat. Yeah. Okay. Historically speaking, an understanding of light first was developed for light as a wave. So we have the wave characteristic of light, and these mathematical equations from James Clerk Maxwell completely described light and its electromagnetic behavior. Right? And they worked. They worked in most situations, at least the ones that they knew of at the end of the 19th century. And they're still valid today, as long as they agree with things like general relativity and quantum mechanics. So sometimes they butt heads. So the scientists at the end of the 20th century said, okay, we got it all figured out. Right? We got all these equations. It wasn't just with light, it was other things. We got it all figured out. So from now on, all scientists are going to have to do is just refine their theories, right? Refine what we know. Wrong. Along comes Max Planck. I think he was a German. And what Max Planck proposed, actually, he was working on a phenomenon called black body radiation. You know that pickle, as you heat it up, it starts to glow. And that's essentially what black body radiation is. Black body radiation is the radiation that comes from any object that is heated to a certain temperature. It doesn't, there are no reactions of the black body to create the light. It's all due to temperature. And that's the way we deduce the temperatures on the surface of various stars. We measure the colors of the star, and the more blue it is, the higher its temperature. Our star, the sun, is kind of a yellow color. It's kind of in the middle range. Right? Red, orange, yellow, green, blue, indigo, violet, right in the middle. So Max Planck was working on this, and he came up with this formula. He says the energy of light that is transferred. I don't know the connection between this and the other, but he was working on that. This developed from it. The energy of light can be expressed as some constant. This is Planck's constant times the frequency. Okay, so if you know the frequency, and you know Planck's constant, which I don't have memorized, then you can calculate the energy, and this will be in joules. Right? So if this is in reciprocal seconds, right? What do the units need to be here? Joules, seconds. Because this is in the denominator, this is in the numerator, they cancel and leave you with joules. Okay. So whatever that number is, the units are joule seconds. No, joule seconds. Joules per second would be in the denominator, and then it wouldn't work because this one's in the denominator already. Yeah. So it's I guess it's what would you call it? A compound unit. There's the Planck's constant, 6.626 times 10 to the 34, negative 34 joules seconds. And the frequency needs to be in reciprocal seconds, or hertz. He also considered the energy of light to be quantized. What do we mean by quantized? That is, it can only have a certain quantity. If it has more, it's got to go up to this level. Nothing in between. It's units from here to here to here to here. That's what quantized means, as opposed to continuous. So now we're starting to get an indication that maybe light is not only a wave. Could be have particle nature too. Oh, I got a...
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also...
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay. So the photoelectric effect is giving us an indication that light is not just a wave. Einstein put the two together, wave and particle nature, and developed a series of formulas that showed it mathematically. All right. Observations of the photoelectric effect. We know that below a certain frequency, it needs to be a high enough frequency, or blue toward the blue end of the spectrum. And it's different for each metal. We're essentially talking about metals here. It needs to be a high enough frequency, that threshold frequency, before you get any electrons at all. Now, if the nature of light were only waves, then any light would do. All you would need to do to eject an electron, if it was only waves, is just make the light more intense, give it more waves, more energy. But that doesn't happen. So once we reach the threshold frequency, then you can eject more than one electron if you increase the intensity. And the intensity just means that you have more light packets per time unit. All right, I already said that. Below that frequency, no electrons are emitted. So once you reach that threshold, then you can make more electrons jump off the metal. And we use the photoelectric effect not just for metals, but we use it for silicon also in photovoltaic cells, which are all the rage these days. What happens though, if you increase the frequency beyond that threshold, then you've got enough energy to eject the electron, right? So there's your metal, and here comes your light, and it's in packets called photons. You got a certain amount of energy, right? And that's due to the threshold frequency. And that's just enough to get that electron to the surface, free from the atoms. Anything in excess of that, if you have a frequency, if you have a frequency that's greater than the threshold, then it's got a little extra energy. And what it will do is it'll take that extra energy and translate it into kinetic energy for the electron. So if your threshold frequency is in, say, the green range, but you give it blue or violet, then you're going to have electrons jumping off there with kinetic energy. And you can measure the kinetic energy with certain types of detectors. Okay. So what can we conclude? Well, the electromagnetic energy arrives at the surface of the metal as photons, right? Packets of light. And each of those packets of light has energy equivalent to Planck's constant times the frequency. We need a minimum amount of energy in order to eject an electron. And that energy is required to cause the electron to jump from the metal to infinity. Here's why I say that. If we have a nucleus here, and it's got protons and some neutrons in it, there are energy levels. Okay. 1, 2, 3, 4, and 5. I've drawn here. Okay, if you have an electron, say it's just hydrogen, you have an electron there. If you add a certain amount of energy with a given frequency of light, it will jump from maybe here to here. Or if it's the right frequency, you can make it jump in a different quantum from there to there. What we mean by infinity is you reach infinity when the electron is essentially removed from the atom. How much energy does it take to go from here to here? And at infinity, the energy relative to the nucleus is zero. Okay. The energy as you get closer is negative. We'll talk about that more in a minute. But to go to infinity, that requires that threshold frequency. Yeah, if you're going from zero, because the energy of the electron is decreasing the closer you get to the.
Yeah, but it increases in the positive direction.
That's because you have to add energy to it. Yeah, right. It's that system surroundings thing. Have we talked about that? Okay.
So
If you define your system, and everything else is surroundings. So when you add energy to the system, that's a positive value. As far as the system's concerned, it's gaining more. Right? If we lose energy, it's negative. So in order for the electron to move from this level to that level, it's moving from a higher to a lower, so it has to lose energy. That's why the values are negative. Okay, you had a question?
Oh yeah, I was just gonna say, so infinity, is that like the zero? Is that like it loses all energy? Like
It has no energy relative to the nucleus. Right. And with the threshold frequency, it's just barely free of the nucleus of the atom. It doesn't have any kinetic energy of its own. It's just kind of like sitting there.
Okay.
If we go to a higher frequency, then we can give it some kinetic energy from this point on. Now, if the photon doesn't have enough energy to reach this 0 point, we call those thermal photons, because all they do is add energy to the atom, and that manifests itself usually as heat. Okay, we talked about that already. Intensity is just a measure of photon density. In other words, if you have light of a certain frequency, intensity just means that you add more photons at that same energy level. You haven't really increased the energy of the light. You've increased the energy density. There are more photons packed into a smaller area over a period of time. Okay, what does this photoelectric effect tell us about the structure of the atom? Well, first of all, the interaction of light with an atom happens with the electrons. It doesn't affect the nucleus at all. Now, the nucleus, of course, controls what the atom is, you know, whether it's sodium or whether it's iron or gold or whatever. But when light strikes an atom, it's interacting with the electrons.
So the particles are the light. Is that what that is?
Yeah, it's a combination, right? The photon particle has waves in it.
That's the particles. Like that's the way.
What's the question?
Like is the particles, is that the way? Like the energy that it
It's kind of like the way they drew it, it was like this. That's a photon. It's discrete, but it has wave in it. It's a combination of the two. That's the way Einstein presented it for the photoelectric effect. So one of these photons with that wave characteristic goes down here.
are you asking the way behind the particles? No, I'm asking is the particles and that what produces the wave because it's like
No, you can't say that one produces the other, right? They're co-equal. They're coexistent.
so
If you produce one, you have to produce the other.
so if the nucleus doesn't matter as far as like which is what makes a certain element a certain element, then how does certain elements make different kinds of light? You know what I'm saying?
Yeah, it's all about the transition of electrons between energy levels. If you have an electron that in an excited state that's out here, and it jumps from one level to the next, it's going to a lower energy. We have to conserve energy, so it gives up energy as light. And
Is it based on how many electrons with them? Like the electrons can vary, but it's based on how much weight is going to be a certain element that's going to cause the element.
well, if we're trying to be quantitative about it, right? The only one that we can absolutely calculate ourselves, energy transformations of electrons will generate this wavelength of light. The only one that we know and can do for sure is hydrogen, because it's only got one electron. Once you get two or more electrons in there, they start to interact. And that
I didn't know like how it would be different, so it's not that kind. It's just
it's empirical.
Okay.
Yeah. Now there's a lot of effort being put into trying to quantify it. And quantum mechanics goes a long way to doing that. But at this level for us, we just have to, I just have to get my reference book. I've got this book, it's about that thick, and it's like this. And you look up the element, and it gives you the emission spectrum of each element, right? Wavelengths and their intensity, right? How strong are they? So we pick out the one that we can use the most, and it's not like any others. And that's the one that goes into our instrument that we use to quantify that element, right? I had an instrument that's called the inductively coupled argon plasma spectrometer, right? And it did that. It took a solution of that we got usually from either an extract of a soil or a digested plant material in the solution form, and we aspirated it into this coil, and the coil was vibrating with very high energy, and it was coupled to argon that was being blown through it. And all you had to do was seed it with a few ions, electrons usually, get it started. And once it was coupled to the magnetic fluxing field in that coil, then it could be maintained. And it looked like a flame, but nothing was really burning. It was just a lot of energy. It operates at about 10,000 Kelvin. And it rips everything apart. You get individual atoms, and then in another part of the flame, they're ionized. And then in the upper part of the flame, it starts to cool. And that's where it emits radiation as the electrons start to fall back. And there you want to pick out the wavelength that separates it from any other element. Some of them are really close together, so you don't want to use those. And then we send that light that comes off of into the optics of the instrument, and it uses usually a grating rather than a prism, but they do the same thing. And you spread the light out into its individual wavelengths. Your instrument's calibrated with slits around a circle, and it's set so that the light comes through and only that wavelength comes through, and it's the electronics of that detector are tied to the computer that runs the instrument, and it says this intensity is due to that element. And if we have more dense photons, lots of photons, then we equate that to a higher concentration of the element. Okay, that's ICAP in a nutshell. All right. So the interaction occurs between light and electrons. And the absorption of a photon of light is specifically tuned to the transition of electrons from one energy level to the next. No in-betweens. Okay, this threshold frequency, which is equated here to threshold energy, is the particular frequency that will take that electron from the atom to infinity. And that's all it's required to get it free of the atom. But if you want it to have any kinetic energy of its own, you need a higher frequency, more energy that will add kinetic energy to the electron. The one thing that we haven't touched on is that we just said that electrons have kinetic energy then. Well, anything with kinetic energy has to have mass. And if you're going to transfer kinetic energy to an electron, that means that the photon must also have mass. Now, that's kind of a difficult concept to swallow, that light can have mass. But Einstein also went and proved this one too. Right? Mass and energy are equated. Right? If a photon of light has energy, it also has mass and equivalent mass. There's my favorite picture of Einstein. He's kind of elderly now. He's already made a name for himself, and so he can, act a little silly if he wants. So Einstein came out with the special relativity theory in 1905. Actually, the year or two before that, he published his paper on photoelectric effect, and that's the one that won him the Nobel Prize. All right, so he proved that light has mass. This is in a relativistic sense. In other words, light's never at rest, as far as I'm concerned. Maybe on a theoretical basis, you could stop a photon. But what we're talking about here is light, of course, is moving at the speed of light. That photon is moving at the speed of light. So it has mass based upon its speed. All right. So Einstein mathematically proved it in 1905, but Arthur Compton came along and confirmed it experimentally in 1922. That's the funny thing about physics. It's broken into two groups that never meet, except where their theories cross. There are theoretical physicists, Einstein was one of them, and experimental physicists, Compton was one of them.
The Compton had won the Nobel Prize.
No, Compton didn't win the Nobel Prize.
They won it.
Oh, they won separate Nobel Prizes.
Yeah.
That was Millikan. Yeah, Robert Millikan. And I think Robert Millikan won his for determining the mass of an electron. Yeah, he tried to prove him wrong, which is perfectly valid in science. You take somebody else's work and say, I'm gonna kick you off your let's see, King on the Mountain. I'm gonna kick you off. Yeah. And it turns out he didn't. He actually proved Einstein was right. So light has a dual nature. It's both wave property and particulate property. So if light can act like a wave or a particle, then any mass can act like a wave because it's already a particle. It can act like a wave. So I have a wavelength, you have a wavelength. Everything has a wavelength. And it's based upon motion, right? And when I'm standing still, I don't have a wavelength. But if I'm moving, I have a wavelength. And that comes from de Broglie's equation. He was a Frenchman.
I was about to say it.
Yeah. So both are correct, wave and particle. Now we know electrons have wave properties, right? They're particles, but they also act like waves. And we know they act like waves because they behave like waves. You've heard of the electron microscope? You haven't heard of the electron microscope? Okay. You've heard of light microscopes, right? You had a bunch of them sitting on the back, right? There's a limit to how small a particle or a structure you can see with a light microscope.
Okay, then
It's called the diffraction limit. And we can't see anything smaller. Well, what you need is something with a smaller wavelength. And that's where electrons come in. So we fired electrons in a vacuum at an object, say a virus, or even, I don't know, a surface of a metal. And we can image it because the wavelength of a moving electron is much, much, much shorter, smaller wavelength than it is for light. That way we can image things with an electron microscope. Now there are various types. There's transmission electron microscopes where you fire it through the object, and there's reflection where you coat the object with reflective thing and fire the electron, it bounces off, and you image it that way. But it's due to the wave nature of this particle, the electron. And we know that the electron behaves like a wave because of this diffraction characteristic. Diffraction is, and the animation there says that when the wave strikes that barrier, the only part of the wave that gets through is through that little slit, that little opening. That opening serves as a point source for another wavefront. So that's what you see radiating out from that point. That's diffraction. If light were a particle only, then the wave would approach like this, and then it would go like that. And if you had a detector over here, you would see it there, but over here, you would see nothing because it would travel in a straight line. Particles travel in a straight line. But you would also, in this case, you would see it at those other angles because it behaves like a wave from that point. Refraction. I didn't mention that one. This is diffraction. And refraction is the bending of light when it transitions from one medium into another. They're both transparent media. It's whatever the light's traveling through.
Okay.
So if we have, say, air here and glass here, glass is more optically dense than air. So if the light beam is coming in at an angle, this is using a ray tracing. If the light beam is coming in at this angle and it strikes the glass, it's going to bend some. That. Okay. Now, how do we measure the angle? Well, the angle is measured relative to the vertical, or in mathematics, we call that the normal. So this angle here, theta, and this angle here, phi, are different. This one's smaller than that one. So when it goes from a less dense to a more dense, it bends toward the more dense. If it went the other direction, it would bend away from it. And well, I've said enough. I've already wasted enough time. So now we're going to try to use what we know about light to gain some insight into the structure of the atom. We talked about energy levels. So we're going to look at hydrogen because it's the simplest one, and because hydrogen was the first element that was used to try to develop a model for the atom. I think I need another.
Do we have a lab to do this?
Yes.
Yeah.
So I got to get finished with this.
Comment to do with this stuff.
Oh, with this stuff?
Yeah.
No, I couldn't find a good one. Now I've got labs that I do with my physical science survey class, but they're all virtual.
Wow.
They're online, and they're just your favorite type of lab. It's just fill them out. Okay. When we look at the spectrum of light of any source, sometimes we see a continuous spectrum. In other words, you can get all colors of the rainbow in one shot. And that's what you get when you look at the sun. But you can also get line spectrum, where you only get single wavelengths in several lines. And hydrogen emission spectrum is a good example of that because it's really simple. Just one electron going through its various transitions. Right, here's a continuous spectrum. This used to be an animation, but it was written in what's that? The code that they don't support anymore. Anyway, but I like the picture, so I kept it. That's a continuous spectrum. You shine it through this prism, and it gives you every color in the rainbow.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay, so what we see is when an electron is dropping from a higher level to a lower level, it's losing energy. And we see that as a different color of light, depending on transition from which level to which other level. And these are all quantized. That is, it only goes from one level to the next, nothing in between. Right? What would happen if it were allowed to go to any level it wanted? We get a continuous spectrum. Right? Any color is possible then, but we don't. So that tells us something about the structure of the electrons around an atom. They occupy certain energy levels. All right. And I just mentioned that the color's not white because it's not a combination of every possible color. It's not continuous. That's I already said that. Those regions between those energy levels have a 0 probability of finding an electron there. The first one? Yeah, if they were not quantized.
Oh.
Yeah. Since they are quantized, we don't see white light. We see line spectra. Okay. The first model that was proposed for, and whenever you see model, think theory. This is trying to explain why we see what we see in those line spectra. Was the Bohr model. Niels Bohr proposed this one. He was a Danish physicist. And his model was based upon the planetary model. In other words, the sun would be the nucleus, and then the various planets would be electrons. And so he said, if the nucleus is here, then the electrons orbit around the atom in various energy levels. And as we get further and further away from the atom, the energy levels get closer and closer together. And he gave each one of these energy levels a number. The first one, of course, not original. And we had 6, actually, that were in that line spectrum. You may have noticed that the electron, when the electron jumped, it never jumped to 1. It only jumped to 2, 3, or 4, or 5. So if you jump to here, you get 1, you get another one, and another one. So you get 4 lines. This is the visible region. Now, that doesn't mean the electrons can't jump from this level to n equals 1. But if they do, the energy is so high that the wavelength is going to be too short for us to see. It's going to be in the ultraviolet region. So you have a series of spectra that are based upon a jump to n equals 1. And you have some that are others that are
So when fire becomes blue, like is this the same kind of thing, or is that something different?
well,
I
we
know it's light, so I didn't know if it would be different if it's one piece.
yeah, the only thing we can say for sure is that it's due to energy
Right.
transitions of electrons.
So it's not because like it.
It's a little more complicated than that when you're talking about a chemical flame
Yeah.
of some kind.
Okay,
Yeah.
So it's not to do with it.
But you can say that the blue light is a higher energy transition, whereas the yellow light is less energy.
It's not like it's related.
And it's a little more complicated than we can tackle here.
Right.
So there you have the transitions. And Bohr said that these electrons were quantized. They move from level to level, nothing in between. That was his planetary model for the atom. And he didn't just stop there. He actually quantified it. Right. Well, what's missing is the 4th line. We only got 3 lines in this one. Should be one going from 6 to 2. Would give us the 411 nanometers. Okay, there's another representation. I want to get to the math. Now, I will say this, the higher energy is toward the violet side. So the higher energy is going to be a larger change in the position of the electron. So if it goes from 6 to 2, that's a greater change than from 5 to 2 or 4 to 2. So the shorter distance is going to give us a longer wavelength, lower energy. So Bohr came up with these possibilities. Let's see, I don't need to erase that. We can calculate the energy of each electron at these levels. All we need is this formula, minus 2.178. 18.
Yeah.
And then times this value, which is z squared over n squared.
Let's see.
It's the same as we learned before. Z is the atomic number. Remember when I draw this, Z is here. That's the number of protons. And then let's see, what was this one? This one's A. That's the mass number. So Z is the atomic number, and then N is the energy level. So if we know the energy level and we know Z, well, for hydrogen, it'll just be 1. So if we put 1 in there and this one, the energy level, we put it whatever it is, it'll give us the value in joules of the energy at that position.
So N is not moles, it's.
No, in this case, right. In this case, N is, this is,
The energy.
I'll go ahead and give it to you. It's the principal quantum number.
These are keywords.
Well, because Q means heat. Yeah. I have no explanation. Okay, so we can calculate the energy at this level. We can also calculate the energy, say, of a lower level. And if you know the energy of the lower level, you can subtract it from the higher level, and you can tell what is the energy of the transition. And then we can use Planck's equation. Once we know the frequency, or the energy, once we know the energy, and we know this is a constant, we can calculate the frequency. Okay. We can also calculate the wavelength if we take this equation, right, and solve it for nu. Right. Then we can substitute this in this one, and that's h times c over lambda. So we can solve for the wavelength or the frequency. Huh? Are we okay? The thing about Bohr's model is it only works for the hydrogen atom or hydrogen-like atoms.
More not people credit out. You know them a lot.
Well, he's done some other stuff too.
I know. They don't hear. I'm not ever talking about his name.
No. Yeah, I mean, sometimes it's a crapshoot.
Yeah.
I mean, people that deserve the Academy Award don't get it. People that deserve the Nobel Prize don't get it.
Mhm.
So, in order to use this equation, your atom can only have one electron. All right? Hydrogen's easy, right? It only has one electron to start with. But if you want to use this equation for helium, right? If you want to use it for helium, then you got to get rid of one of those electrons, right? Because it's got 2 electrons. So if you get rid of one electron, it's going to be a +1 charge. And that will work for this also. If you want lithium, right? Lithium's got 3 electrons. So it has to be a 2+ charge in order for it to work. Only hydrogen-like atoms are going to be useful. So in that case, you would put a 2 here for helium and a 3 here for lithium. As long as it's the ion, the proper ion with only 1 electron, then you can use that formula. That's one of the major limitations of Bohr's model. It only works for hydrogen. Okay. Let's see. Now, if you want to calculate the energy of transition, you need to subtract the initial from the final. Remember, that's always the way. When you see a delta anything, it's initial minus, final minus initial. Minus initial. It's that with temperature change, it's that with volume change, it's that with the energy change, it's that with whatever. So that's why we have final first calculation, then we subtract initial. So we can reduce this, right? We can factor out we can factor out that constant. Right? If we do that, then we have to pull the constant out. This is algebra. Pull the constant out, and we've got z squared over n squared final minus z squared over n squared initial. And for the hydrogen atom, z is 1. Right? So we just stick the 1 in there and go from there. Okay. For the hydrogen atom transition from 5 to 2, here, down to 2, produces blue light of a wavelength of 434 nanometers. So what's the question? Well, what's the energy? The energy transition there would be this formula. Right? We can plug in the final is 2, the initial is 5 because it starts high and goes low. What if we went the other direction? What would happen? It would be the same wavelength, but it would absorb that wavelength. So if we had hydrogen in the atomic state in this container, and we shone a white light through it with all wavelengths, it come out the other side, it wouldn't be a bright line, there'd be a dark line because it would absorb that wavelength. So yeah, because it goes both directions. No, there wouldn't be any light there. It'd be all light here, dark. Yeah, yeah. That's how helium was discovered first in the atmosphere of the sun. Huh? For hydrogen. Yes, for hydrogen. If we had a different element, right? Okay, so in this case, we're emitting light. So the final is going to be the smaller, the 2, and the initial is going to be the 5. And we get that many joules, 10 to the minus 19th joules. If we calculated the wavelength, right, we put it into this formula right here. E equals that. And actually what we're doing is comparing, if we use that one to calculate the energy of, let's see, of 434 nanometers. That's what we're doing here. So we take 434, it's equivalents to meters right there. Plug it into that formula, and we get 4.577 times 10 to the minus 19th joules. So it's very close. Right? We have to go to the second decimal place to get discrepancy. That just proves it works. Yeah, this is my chapter 7. Yours is 6 and 7. Yeah, 6 and 7. That's why I put this up here. Because I don't know why Brown decided to split them into 2. Maybe they split it into 2. Cover one chapter is this and the other chapter is that. But in my textbook and my slide set, they're all in one chapter. So the Bohr model correctly fits a quantized energy level format as long as we use the hydrogen atom. And as this value gets smaller, this value gets more negative right? Because if this is 1, then it'd be that value. If it's a 2, we divide it by 4, and it's at a higher energy, it's less negative. So the more negative it is, the closer it is to the nucleus. Model only works for hydrogen. The other problem is he assumed that the electrons move around the atom in circular orbits. Right? Well, if that were true, what happens to satellite in orbit? It gradually deteriorates, right? It gets closer and closer and closer and burns up in the atmosphere, right? But electrons don't do that. I mean, they're at these energy levels, they stay there. So we need another theory, and that's coming. So what color of light is emitted for these transitions? Well, the larger the jump, the shorter the wavelength. Right? The higher the energy, shorter wavelength, higher frequency. So this one's going to be the violet. The next jump is not quite as big. It's the blue. The next jump is a little bit less energy. And then the lowest energy is orange-red, between 3 and 2. So between 3 and 2 is the lowest energy for this set of wavelengths. If we jumped between, say, 6 and 5, then the wavelength would be one we couldn't see. It would probably be in the infrared. Come on. There we go. That one has the, oh, yeah, I messed up my animation. I need the question first and then the answer. The longest wavelength, of course, would be the orange-red. All right. Now we come to a smarty named Werner Heisenberg. All these guys knew each other because they were working around the same time. And they had meetings, scientific gatherings. Heisenberg, and this is a simplified version of Heisenberg's uncertainty principle. The thing about when you start to deal with things this small, it's difficult to say with definitely where they are, how much energy they have. So Heisenberg went to work and proposed this approach. He says that delta X means change in position. Can you detect a change in position of the object? In our case, the electron. Or can you detect a change in the momentum? That's the Greek letter rho. In their slide, rho is mass times velocity. Okay. Whatever this product is, a change in this one, change in that one, it has to be greater than Planck's constant over 4 pi. So this is a constant value. So what do we know about constant values? If they're equal to, if the product is equal to, then they're inversely proportional. Yeah. So if this one has a big variability, large difference in position where it is, in other words, we don't know where it is, then this one is small. So we can say something about its velocity or its energy, right? Because the mass is going to be the same. But if there's a large change in momentum somehow, a large change in velocity, then this will become small. And then we can know where it is. But you can't know both at the same time. That's what Heisenberg is saying. And this, not really an equality, but this value calculated here is greater than Planck's constant divided by 4 pi, means that you can say the same thing about me or some other object. But, right, This is very, very small. Change in position. You know where I am. And since my mass is really large, then this can be small too. So the larger, what I'm saying is, the larger the object, the more likely it is for us to determine both this and this with accuracy, because those values will exceed this value. But when this gets really, really small, its mass gets really, really small, then it's more difficult to exceed that value with both of them being known for sure. So we have to say, when it gets small, like an atom or an electron, you can't know where it is and how fast it's moving at the same time. These are other people that were working on this problem at the same time. Right? Just wanted to give them credit. Hat tip to these guys. I think it was Heisenberg worked on this. Or actually, it came out of Schrodinger. Schrodinger. This is Schrodinger's work. You ever heard of the, let's see, what is it called? The cat in the box experiment? You haven't heard of that? Yeah. I won't bore you with that one then. It was Schrodinger's idea. Schrodinger came up with a series of equations, and he ran it by various of his colleagues to be sure if they thought it was correct. And what came out of it was the quantum theory, quantum mechanical theory of the atom. And part of that theory was this wave function. And so now we're treating the atom as having wave properties. And this particular symbol, and we square it, this is the Greek letter psi. Right? If you go to a university and drive down a sorority row or fraternity row, you're likely to see a psi somewhere. It's in their Greek letters. But for our purposes, this references the probability of finding an electron in a certain place in space. If this value is high, then we have a high probability.
Do you use our letters in their time?
No, we use Greek. We use Greek so that we don't get it confused with other things. Because the Greeks, no, they use Greek letters. Right. Greek scientists, you mean? Yeah, no, they use Greek. It's a small country. They don't have much clout, so they have to do what we tell them. I mean, they started the ball rolling like 3,500 years ago. But since they've kind of lost their clout. So the point of this is, since we can't know exactly where the electron is, we'd rather know its energy or its change in momentum, its velocity, something about its energy. We'd rather know that with certainty. Then what we do is we approach the position of the electron in probabilistic terms, right? It's probable that it's going to be in this region. It's more probable it'll be here, less probable here, no probability that it'll be here. That's what we're saying. So we're taking Heisenberg and sort of backseating the position of the electron and focusing on its energy, because that gives us more useful information. This is a probability distribution of 1s wave function. Now we haven't done the electronic configuration of an atom yet. Okay, right. So you won't know what 1s means. This is a better representation, right? The distance of the nucleus. This shows us the probability of finding an electron in that region. So at a certain distance, the probability is very high. A distance further away is less probability. And of course, it should go down to 0 because electrons don't exist right next to the nucleus. They're at a certain distance from the nucleus. Okay. This particular the n equals 1. Let me start it off now. So if we're going to start talking about quantum mechanics, in order to draw the electronic configuration around an atom, then we need the quantum theory. Actually, the quantum mechanical theory. And in Schrodinger's equations, let me see, how do we spell his name? I can't even remember. SCHRO. Schrodinger's equations, you need 4 numbers. And those 4 numbers are unique to each electron in an atom. You put those numbers into his equations, and you can tell things about it. Like, what's the energy level? What's the shape of where you are likely to find it? What's its orientation in space? Is it pointed this way or is it pointed that way? And we're still talking probability, right? It may be pointed that direction, but it could be any place in this region. So we need 4 numbers. The first one is grandfathered in from Bohr. So n is the principal quantum number. And it tells us basically something about the energy at that number. The energy is a certain value, and about the size. So the higher number means the energy is going to be higher relative to the nucleus, because you got to add energy to get the electron out to that position, and the size, which means it's got to be bigger. And that's what this one is for. And you can have numbers here from 1 on up to whatever highest number. Okay. That's the principal quantum number. The angular momentum quantum number is L. Quantum number. This one is based upon any one of these. It's kind of like a branching tree. Right? You start from N, you go to N somewhere, and then you have several possibilities of L at that particular N. So it builds on itself and branches out. This one, the angular momentum, speaks to the shape of the orbital. Right? Is it spherical? Does it have lobes on it? Is it like a donut? Various shapes. And these are all mathematically driven. Right? They're not observation. We don't observe these things. We have evidence that they're probably right because they do explain certain behaviors. The possibility for numbers here is you take the n and you start from 0. 0, 1, 2, on up to n minus 1. So if n were 3, then we could have L possibilities of 0, 1, and 2. Because that's n minus 1. Okay? Then you get the magnetic quantum number. That's the next one. Magnetic quantum number refers to the orientation in 3-dimensional space. Okay. And the magnetic quantum number is based upon any one of these numbers. So if we had a 2 here, actually it goes from minus L through 0 up to plus L in whole number increments. So if we had a 2 here, then the m sub L possibilities would be -2, -1, 0, +1, and +2. Have 5 possibilities at that L. Okay. And then the last one is the easiest one. This is the spin quantum number. And it can be either +1/2 or -1/2. And this talks about it treats the electron as if it were a spinning top. So it can spin this way or it can spin that way. Okay, those are the 4 numbers. If you have a number here, and then a number here, and a number here, and a number here, then that is unique for that electron. And plug it into the equation, and that tells you something about the energy, the shape, the orientation, and which electron is it, right? So if you have one of these, you're going to have 2 electrons at each one of these levels. One going one way, one going the other. Okay, those are the quantum numbers. If that hadn't made your head spin around, then I don't know what will. We're going to use that information to draw out the electronic structure of atoms. Okay. I don't know how useful this table is. In fact, I'm inclined to skip it and go to actually using these values, and it make more sense, I think. But it's there if you want to look at it. Oh, by the way, in many books, this is often referred to as a shell. And this is referred to as a subshell. And this is referred to as an orbital. Okay, in case you see that in your textbook, and that's what it means. Okay, so let's see. If we have a principal quantum number of 3, n equals 3, and determine the number of allowed subshells. These many. How many of these can you have at 3? Yeah, different values of L. Okay, so if n equals 3, then L could be what? It could be 0, right? 1, or 2. You go start from 0, take n here. You start from 0 and you go to n minus 1. So you can actually, if you have n equals 3, you can only have 3 levels of L. Oh, by the way, when we start drawing out these electronic configurations, it's going to be difficult to write just numbers, because numbers can get really confusing, like you forget a comma somewhere. So what we've done is we've given these numbers, the L numbers, letters. So if we go from 0, 1, 2, 3, 4, 5, this is the S. If L equals 1, it's a P, SP, D. This is an F. And this is as far as you're going to need for neutral atoms. To go up to 4 and 5, you have to excite the electrons. But they're there. Right? They're available, G and H. But you're only going to need these to understand how the periodic table is structured.
So that L would be S and D.
Yes, this would be possibilities of S, P, or D at n equals 3.
Why
Why what?
don't the second number?
Oh, because when you start writing out the configuration, right, how are you going to keep the numbers separate from one another, right? Because when you're identifying an orbital, then you come out to here, and S can only have 1, right? It can only have m sub L. This can only have 1,
Oh,
right? Because it's right -0, 0. This one can have 3, right? It can have -1, 0, +1. This one can have -2, -1, 0, plus 1, plus 2. Those are allowable numbers. We're not saying that one electron has all these numbers. We're saying those are allowable. It hopefully it'll become clearer when we actually take one of those elements and write out its electronic configuration. Which is what I want to do in just a second. The further down you go, the longer it gets. Yeah. All right. So let's take this example. Suppose, it doesn't matter what this one is. Suppose we go down here and say, if L equals 2. L equals 2. Then determine the magnetic quantum numbers for M sub L. I think we already did that. M sub L would be -2, -1, 0, +1, and +2. There'll be 5 orbitals. All right. How many electrons does that represent? If you can have +½ or -½ at each one of these levels, you could have 2, 4, 6, 8, 10. 10 electrons. So you could just with this set of orbitals, you can have 10 elements, because as you add one proton, you add another electron. So we just keep adding, and we can have 10 elements. Notice how many elements there are across the transition elements. 10. So the transition elements are filling L equals 2, right? D orbitals. That's just a hint. Notice that if we have n equals 1, 2, or 3 in this case, but we're saying the L for each one of these is 0. It's an s orbital at any one of these levels. They have the same shape because they're all s's. They're all spherical. But there are some differences. Right? If the s is from the n equals 1, then it's a solid sphere, more or less. If n equals 2, then it's a sphere, but the internal structure is slightly different. In other words, there's a node in there. A node is where the probability drops to 0. Right? So if you look at it here, there's no node in 1s, but in 2s, you got a node there. And in 3s, you got 2 nodes. So the shape is still the same, but the internal structure is a little different. Okay? That's important for some of the next concepts once we get past this. P orbitals are a little different. P orbital shape, rather than spherical, is dumbbell. And then if we go to the magnetic quantum number, if L is 1, let's do that. If L is 1, that's a p orbital. And we can have -1, 0, or +1 for the M sub L. What that represents, and what we're trying to say here, is that the probability, the density probability for finding an electron in that region is, you can equate it to an XYZ coordinate. And of course, the Z goes back into the board. So you can have -1, say, would be like that, 0 would be like that, and +1 would be like that, back into the board. So that's the orientation in 3-dimensional space. And the d orbitals get a little quirkier, right? There are 5 possibilities. So they're dumbbell shaped, but they don't lie on the axis until you get to this one, and then you get a donut. Now these shapes, like I said before, these are probabilities. These are mathematical derivations. They're not observed, not directly observed. And then F is even weirder, right? F is what? F is 3. So you can have -3, minus 2, minus 1, 0, and 3 more. This is 7. You can have 7 orbitals at that level.
No, that's not-
Huh? Yeah, you can have, if L equals 3, then you can have 7 M sub L's, and each one of those can have 2 electrons, so there's 14. Right. So if you look at the actinides and the lanthanides down there in the bottom row, there are 14 elements across there. So the actinides and lanthanides are filling F orbitals. Okay. Electron spin, of course, is plus 1/2 minus 1/2. So each one of these here can have 2 electrons in it. That means 14 electrons here. Maximum. The Pauli exclusion principle. We saw his name a little bit earlier. The Pauli exclusion principle simply says that in any atom, no 2 electrons can have exactly the same set of 4 quantum numbers. They can have the same N, L, M, but they'd have to have 2 different spins. Or they could have different L's and the same everywhere else. But they have to be a unique set of 4 numbers. Okay. So what's the problem with polyelectronic atoms? Well, that's most of the periodic table. In fact, all but one. Right? Hydrogen excluded. The rest are polyatomic. And polyelectronic, excuse me, polyelectronic atoms. The problem is that when you get more than one electron in reasonably close proximity, you get the repulsive effects. Right? We don't know how these electrons are moving. Right? We chose to focus in on energy and these 4 quantum states. We're not saying a whole lot about actually where they are. We're saying this is the region that we'll find them. So we can't say with any certainty what type of repulsive forces are being experienced by any one electron, again, with its neighbors. We can't calculate them exactly. But we can say other things. One is when electrons go in, as we add protons, right? As we increase the number of protons, and for each proton we add another electron, because we're working from neutral atoms first. So as we add a positive, we need a negative. So we have a number of electrons out here somewhere. As we do that, we know that for any one of these, we know that the electrons prefer to go in lowest energy first. And if this one's occupied, we move up. But also down here, as we enter an S, if that one's filled, then we have to go to the P. If that one's filled and it's available, we go to the D. So we fill in that order also. So we do know that much about how electrons enter the atoms as we start to build them with more and more protons. Now, what we would expect is this, right? The 1 or the 2 or the 3 give you a general idea of the energy of the electrons. Notice they're not exact, but this is the way they would be. The P is a higher energy than an S. And the D is a higher energy than the P by just a little bit. When you start putting electrons into them, then those energies shift because of those electron interactions, and also the effect of the number of protons on them. So this is the starting point. We'll talk about where that takes us in the future. But first, I want to talk about this concept called the penetration effect. And this is not a concept that that is akin to, say, the murderer penetrated the victim's body with a knife to a depth of 6 inches. It's only vaguely resembling that. Penetration effect is still, we have to deal with probabilities. So what we're saying is that, for example, a 2s electron penetrates to the nucleus more than one in the 2p orbital. That is, when we look at the probability distribution of a 2s electron, the biggest spike in the energy for the 2s is out here, and the biggest spike for the p orbital is actually at a lower energy. But the 2s also has, remember, it has a node, so it drops to 0 and then it comes back up closer to the nucleus. So it penetrates some of its electron density closer to the nucleus. And that gives the overall energy signature of the 2s orbital lower than the 2p. And that's due to the penetration effect. What that does is it causes the electron that's in that orbital, the 2s orbital, to be attracted more strongly than the electron in the 2p orbital, because the p orbital can't get that close under any circumstances to the nucleus. Let's see, I think I've got a drawing here. There we go. So if we look at this drawing where the probability of finding an electron is on the y-axis and the distance from the nucleus is on the x-axis, then you notice that the p orbital has one hump closer than the big hump for the s orbital. But the s orbital penetrates closer to the nucleus with that small hump, and that gives it lower energy. That's what we mean by penetration. When we say the 2s electron penetrates closer to the nucleus than the 2p. And in general, say if this is an example of a 3s orbital, it's got 2 nodes, but it also penetrates with the 2 lobes closer to the nucleus than, say, a 3p. Right? So there's a 3s, 3p, and 3d in diagram, and you notice that the 3s has penetration here and here. The 3p is the big lump is closer than the 3s, but it only penetrates down here, whereas the 3s penetrates even closer. And of course, the 3d has its big hump closer than either of them, but it doesn't penetrate at all toward the nucleus. So that explains why the 3s is a lower energy than the 3p, which is a lower energy than the 3d. All right. Now what we're going to do is take a look at the periodic table. Okay. First, a little historical background. Yeah. What we're talking about here is patterns. Patterns in element behavior. They were first recognized that we have records of by Johann Dobereiner. I think he was German. In the late 18th century or the early 19th century. What he found was triads. In other words, groups of 3 elements that had similar behavior. And we use here as our example, the halogens, right? Chlorine, bromine, iodine. They behave similarly in chemical reactions. They're not exact, but they're similar. And there were other triads that he developed, but that's as far as he went. He just identified them and let it go. Then along came Julius Lothar Meyer. We'll talk about Mendeleev in a second. Meyer conceived of a periodic arrangement of elements. Well, I guess we need to introduce Mendeleev too. Mendeleev was working in Russia. Meyer was working in Germany, and they both had similar concepts about the periodic arrangement of elements. Okay, when we talk about periodic arrangement, if we look at the periodic table, right, I'm going to draw out a rough diagram here. Let's see. Like this, down here like this, across here like this, up like that. Okay. Groups are vertically oriented. Elements in the group have similar behaviors, at least on this side and on this side. It gets kind of squirrely in here. But they noticed that these groups only lined up when, as we're adding elements by increasing the number of protons and electrons. When we're adding them from left to right, then we get out here, and if we put one out here, it looks like this group over here, right? So we don't need to go any further. We just circle back, as they say, circle back and put it down here in the next period. So we got periods here and here and here. And so that's what's known as a period. We go to the end, and then instead of hanging off the end of the falling off the edge of the earth, we circle back and put it in this one. Now it's in its correct group. And the only way we can do that is if we use this idea of the period. It's derived from physics, periodic motion. Right? If any of you have had physics, you'll know that periodic motion is still motion, but it doesn't go anywhere. It's like a pendulum on a clock. Right? Weight down here, and it moves backwards and forwards. Right? If it goes up and back and here, that's one period. So we've gone down here and we've gone back to here again. That's one period. All right. So Meyer and Mendeleev conceived of this idea of periodic arrangement of the elements in order to maintain their groups. But Mendeleev is given more credit for his arrangement and his version of the periodic table for a very significant reason. What Mendeleev did was, if he found a position in here where the next element that we knew of, that had been identified, would be here, but it didn't fit with the group. So instead, he moved it over to the next one, which is usually where it would behave like that group. And he left blanks in his table. And not only did he have blanks in his table, but he predicted the physical and chemical characteristics, elements that would go in that position. He said, one day, somebody's going to find that element and it's going to fit that hole. And his predictions came true. That's why Mendeleev gets credit for the periodic table more so than Meyer does, because he used the periodic table to predict the existence of undiscovered elements. Now, the periodic table is arranged with groups, vertical groups, and horizontal periods. And increasing atomic numbers or numbers of protons from left to right, top to bottom. Now, I left out these two down here. Okay. We can also subdivide the periodic table into these 2 columns here and these 6 columns here. Those 2 together are known as representative elements. These are known as transition elements. Of course, you probably already know a lot of this stuff because if you did the extra credit, then you had to fill these things in. These are alkali metals. These are alkaline earths or alkaline earth metals. Okay. These are halogens. Well, these are noble gases. These are halogens. These are chalcogens. Right? These next group are nicogens. The chalcogens start with oxygen, the nicogens start with nitrogen, halogens start with fluorine, and the noble gases start with helium. And that's all we have. Down here are lanthanides and actinides. Okay, and these 2 fit right in here. Okay, that's a general outlay for the periodic table. Now the numbers, the group numbers here, they're using the old system in this slide. So lots of times they have Roman numeral 1A, 2A, 3A, and so forth. Go all the way over to 8A. When you get down here, we use B's. Or you can just number them from 1 to 18 all the way across. Actually, this old system gives us a little more information. All right. Metals versus nonmetals. Right, if we start here, right, with boron and aluminum, draw a line there, and then zigzag elements like that. Then we're subdividing the table into metals and nonmetals. So metals are over here, and nonmetals are over here, which means that most of the table is metals, very few nonmetals. But there are a special group very close to this dividing line that are called metalloids. And that's because depending on the chemical environment and the reaction, sometimes they behave like metals and sometimes they behave like nonmetals. Those are metalloids. Probably the most useful one, as far as we're concerned, is silicon, because all of our electronic technology is based upon silicon. That's why they call it Silicon Valley out there outside of San Francisco, where they do all computer stuff. All right. Now, we need to learn how to build atoms. First is the Aufbau principle. All it says is, as you add protons and 1 electron each for each proton you add, as you're building atoms successively, building elements, the electrons always go into the next available lowest energy orbital. So if we were to write the electronic configuration for oxygen, which has 8 electrons. Remember, n equals 1. N can be 1, 2, 3, on up. L can be 0 up to n minus 1. And then m sub L can be m sub L. Can be anything from minus L to plus L. Okay? So if we have n equals 1, which would be the lowest energy n number, what does it have available? Right? If it's 1, then it can only be 0. That's it. You're done. N minus 1 is 0. So, and 0 is S, P, D, F, 1, 2, 3. So that's where we start, 1s. Right? Then we can put 2 electrons in here, right? Because plus 1/2, minus 1/2. Then we can go to the next 2, right? 2 can have an S, but now 2 can have a 0 or a 1, 0 or 1. So it can be 2s and 2p, right? Again, we can only put 2 in this one, plus 1/2, minus 1/2. So we've used 4 of them already. We need 4 more, right? How many can you put in a p? Well, p is 1, and we can have minus 1, 0, and plus 1. So you can have 3 orbitals in that subshell. Okay? That means that you can have 2, 4, 6. You can have a total of 6 electrons. We only need 4. Right? So we can put all 4 electrons in that p orbital. So that would be the electronic configuration for oxygen. All right. Hund's rule is another one. The Aufbau principle, and then Hund's rule says that when we go to this orbital level, the lowest energy configuration is one with the greatest number of unpaired electrons. When you pair electrons, they get close together and they repel one another, which increases the energy level. So you want to decrease the energy level as far as possible. So if we were to put those 4 into these 3 levels, then we would put one with a spin up. That's how I say plus or minus, spin up or spin down. Then we put the next one in this orbital, not paired. Then we put the next one in that orbital, not paired. We got 1 more electron. It has to be paired. There's no option. So that would be the orbital assignment for these electrons. 2 paired and 2 unpaired. All right. That obeys Hund's rule. And that's what it would look like. The authors of these slides like boxes and double-headed arrows. I like lines and single-headed arrows. It's quicker. All right. What do we mean by valence electrons? Valence electrons are those electrons in the highest energy level for the atom. So they would have the same principal quantum number, and it would be the highest principal quantum number available in the configuration. So in this case, we've got 4 and 2. We have 6 valence electrons. Okay? This also corresponds to the group number in our old system. Remember when we had Roman numeral 1A, 2A, and then 3A, all the way over to 8A. Right? So with 6 valence electrons, oxygen should be in 6A. Okay, that's why this old system is so useful, because the numbering system tells you how many valence electrons are in that atom. And there's our example. All right, so that's 6A right up here. That's where oxygen would be, right there. Here's what we're also showing from the periodic table. As you're adding electrons, notice that this one is hydrogen right here. It only has one S. Right? This one is helium, right? It's kind of out of place. We put it over there because it belongs with the noble gases, but we're not filling, we're filling a 1s orbital over here. So it can have 2 electrons. Now, once we get past that little glitch, each one of these, in these 2 columns, the alkaline metals and the alkaline earths, they're filling s orbitals. Right? Once you get those s orbitals filled, you're done. Now, it could be s orbitals here, it could be s orbitals there or there. It's still filling s orbitals. On this side, these 6, you're filling p orbitals. Notice that there are 6 groups. How many electrons maximum can you have in p orbitals? 6, because there are 3 sublevels, right? -1, 0, +1, 2 electrons each, 6 electrons, 6 groups. S orbitals, you can only have a +1/2 and a -1/2 spin, so you can only have 2 groups. That's why you only have 2 columns here for the s orbitals. D orbitals. Right? D orbitals have 2. Right? So 2, if D equals 2, how about, what's the M sub L? It can be -2, -1, 0, +1, +2, right? 5 orbitals with 2 electrons each, 10 electrons, right? So as we're building, we can have 10 protons with each have an electron. So if we're filling d orbitals, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the structure of the periodic table is built around the orbitals that are being filled in the outermost shell. And then f orbitals down here, right? If f equals 3, -3, -2, -1, 0, +1, +2, +3. That's 7 orbitals with 2 each is 14. And if you count your squares, the lanthanides have 4 here, actinides have 4 there. It's 14, excuse me, 14 there, 14 there. Okay? So now we're getting an idea. We can use the periodic table to build atoms because of the way it's organized. All right, this little device is one way that we can use to be sure that we get those orbitals in the correct energy level. Notice, let's see. Notice that this filling order right here, okay, so we line them up, n equals 1, 2 through 7, right? 1s, we can only have an s orbital there. N equals 2, we can have an s and a p. N equals 3, we can have spd, right? 0, 1, 2, 3, 0, 1, 2. 4, we can have 0, 1, 2, or 3, f. And 5, we only go to f, so we stopped across there. And then we write in the possible orbitals and how many electrons they can have. And then we take a diagonal, this 45-degree diagonal, and we can fill, we do 1s first, 2s next, 2p next, 3s next, 3p next. And then instead of going to 3d, this is where that polyelectronic interference comes from. the energy level for 4s is lower than 3D. So we go down to 4s and back to 3D. So if we wrote out the possible configuration, we'd have 1s, 2s, 2p, 3s, 3p, and then 4s, and then back to 3D. And this device will keep you in the right energy order. Right? Where do we go from 3D? Well, we go back to 4p, right? 4s, 4p. And then we go to 5s. And then we circle back to 4D. And then we get 5p. So it kind of gets messy in there, doesn't it? And then 6s, and so on. But that's the energy level as we increase energy levels. And we know from previous examples, you can only have 2 here, 3 there, 3 orbitals here, 6 electrons, 2, 6, 2, 10. We don't have any F's yet. Okay, this is one way to do it. The other way is to use the periodic table. We're going to draw those things. Okay, let's go back to the periodic table. Notice that as we build 3s, then we go to 3p, and then we go back to 4s before we get to 3D, 4s. Then we get to 3D in this period. The 4th period has 3Ds in it. Then we go back to 4p. Then we can fill with 5s, 4D, 5p. So as you progress left to right, top to bottom, you go through this same sequence in the periodic table. So if you know the periodic table structure, you don't have to remember that. It'll tell you. All right, so let's take an example here, sulfur. Sulfur. So we look at how many protons and electrons does sulfur have? Looks like 16, right? Okay, we know only 2 here and 2 there. That's 4. 6 here, that's 10. We got 6 more to go. 2 there. And we got 4 more to go. 4 there. Okay? Notice that we don't need the rest of these. That's it. Notice also, what was oxygen? Remember oxygen? 1s2, 2s2, 2p, 4. Notice for the outermost orbital, the p orbitals, we have 4 for oxygen, and we have 4 in the 3p orbital for sulfur. And they're in the same group, oxygen, sulfur. Okay, that's why they have similar behavior. They have similar orbitals, and they have the same number of valence electrons, 6. Okay. This also shows you a shorthand method. Notice that if we go from here to here, that's the same as neon, right? 2, 4, 10. So in order to simplify this, we say neon, and then we pick it up after that, 3s2 and 3p4. And that would be a shorthand version of the electronic configuration for sulfur. Why do we use neon? Because neon has completely filled orbitals. Right? That's full, full, full. And these guys are the valence. So when we use this method, we go back until we back up till we're below, start to get below the valence shell. And then everything back here is the same as a noble gas. All right, how about barium? All right, let me erase this, that, and let's clean these up. All right, let's do barium. Barium is a big atom. Barium has 56. All right. So 2, 2, 6, 2, 6, 2. 10, 6, and 2. See how many we got so far? 2, 4, 10, and then 2, 4, 10, and then 10, right? And then 8. How many is that? 38. So 38 from this one is 16, right? No, 18, excuse me, 18. Yeah, 18. So I need 18 more. That's 10, 6, and 2. All right. That would be barium. But notice that this is the valence. It only has 2 valence electrons. Right? In the second column, all the members of the second column, the alkaline earths, have 2 valence electrons. That's why when they ionize, they prefer a 2+ charge. Right? We learned that early on. This is why. And then this part, we take the periodic table and we back up. We back up from barium to cesium to xenon. And this one represents xenon 54. Then we tack on this part, and that's also barium. That gives us the information we need. We only need to know that it has 2 valence electrons to predict its behavior. Europium is 63, and it has f orbitals in it. Right? I'm not going to mess with f orbitals. This is just for illustration purposes. What you find is that europium is a lanthanide. So what it has is the xenon base, plus it has the barium 6s2, but then you get down into the f orbital filling, and you got 7 f electrons. All right. Let's see if I can manage this. All right, we're going to look at some periodic trends in the tables, in the periodic table. We're going to have to define what they are: ionization energy, electron affinity, and atomic radius. And these definitions are critical. Say we have an atom or an element, and we want to find out how much energy does it take to remove 1 electron, right? Send it to infinity. How much energy does it take? Well, what we don't want is to put energy into the element just to get it to change a phase, right? Go from solid to liquid or liquid to gas. So that's why we start with a ground state atom in the gaseous state, right? It's not ionized, but it's gaseous because now, from now on, the energy we put in goes into the electron, not into phase changes. Then what do we get? Well, if we remove 1 electron, we get a single positively charged gas. That's the expression for any ionization energy. Now, this will be the first ionization energy, where we remove 1 electron from the neutral ground state atom. You can also do a second ionization energy if we take this one right here and remove another electron, if it's available. And this will have an enthalpy for it. This will have an enthalpy for it, right? Each one. Well, they give it an I. That's okay. What this slide also shows you is that when you remove 1 electron, it takes a certain amount of energy per mole. When you try to remove the second electron, you're trying to remove an electron from a positively charged nucleus, from a positive balanced atom. So it's more difficult to separate a negative from a positive when it's in this state. So this would be higher energy. This would be less energy than delta H2. And this would be less energy than delta H3. In this case, for magnesium, notice that the energy required for the second ionization is twice what it was for the first. Right? And that's a fair trend. But where do those electrons come from? Magnesium has 3s. Magnesium, let's see, 12. And it would be neon, 10, and then 3s2. So if we remove those two electrons, right, they take a certain amount of energy, but these are the valence electrons. If you try to remove a third electron, you're getting down into what we call the core, into this noble gas configuration. When you try to move an electron from a core, then the energy required goes way up. And that's what we're showing here. It goes from 1,400 to 7,000 kilojoules per mole to make that third electron, because now it's coming from here. All right. So in general, the trends for our periodic table are that from left to right in a period, the first ionization energy increases. So we get an increase in ionization energy from left to right. Why is that? Well, notice we're in the same period. Principal quantum number is 1, 2, 3, 4. You're adding more protons and you're adding electrons to that principal quantum level. So you're not moving the electrons significantly farther away. What you're doing is increasing the nuclear charge. You're making more positive charges in here. So the outermost electron is feeling a stronger pull. And in fact, it'll shrink the atom. So that means that the first ionization energy, as we go from left to right, increases because of that increasing nuclear charge. As we go from top to bottom, the ionization energy decreases. Why is that? Well, even though we're adding protons to the nucleus and increasing the nuclear charge, we're also adding electrons to higher energy levels. So the outermost electrons are further away, plus they've got all these electrons in between shielding them from the nuclear charge. So that shielding effect decreases the amount of energy required to remove the outermost electron. All right, so when we combine the trend, we would increase this direction and increase that direction. So the trend is from lower left to upper right is increase. First ionization energy. Okay. If we go across the periods, what we notice that in general, we get an increasing ionization energy, but there are some anomalies in there. Right, when we go from, say, beryllium to boron, beryllium is losing electrons from the s orbital, whereas boron is losing electrons from the p orbital. The p orbitals are further out, right? They're lower, they're actually higher energy, So it takes less energy to remove a p orbital than it does an s orbital electron. So as we go from beryllium here to boron there, now you're removing that first electron from a p orbital. It takes a little bit less energy. Not much, but it's measurable. Also, when you go from nitrogen to oxygen, you get a decrease in energy required for the first ionization energy for oxygen. The best way to explain that is to look at their electronic configurations. Let's put nitrogen first. Nitrogen is 7, oxygen is 8. So we have a 1s2, 2s2, 2p3, 3, 4, 5, 6, 7. And then oxygen is 2s2, 2p4. Okay, the way to understand this one is if you have a drop in first ionization energy here, the electron that's being removed must be at a slightly higher energy because it takes less to get it away from the atom. Okay, these guys don't tell us anything right here because they're paired like that, like that, like that, like that. But when you get to P, you've got these 3 orbitals, and nitrogen has 3 unpaired electrons, but they're separated from each other. Whereas oxygen has 4. That electron right there is in the same orbital as the other electron, even though they're opposite spins, but they're still pushing on each other. There's a repulsion there. And that slight repulsion allows you to remove that electron with less energy. That's why we get that dip from nitrogen to oxygen. And you can see that trend across, it shows up occasionally. Once you start getting into the transition elements, like down in here, right here, and here, then you have different explanations for those. We're not going to get into them just yet. Okay. Explain why the graph of ionization energy versus atomic number across a row is not linear. Where are the exceptions? Electron repulsions is a major factor, and difference in orbital energies. I left that one out. Electron repulsions is good for nitrogen, oxygen, but from beryllium to boron is a difference in orbital energies. All right. Which would require more energy to remove an electron? Sodium or chlorine? Well, let's look at our periodic table. Right. Sodium and chlorine are in the 3rd period, both of them. So the trend is from left to right, we increase the ionization energy. And so sodium should be lesser than chlorine. Chlorine would be the larger requirement for energy to remove that first electron. How about lithium and cesium? Well, lithium and cesium are in the same group. Cesium's way down here, lithium's way up here. It takes more energy to remove lithiums because the electrons are closer to the nucleus. Plus, cesium has a lot of electrons between the outermost electron and the nucleus, so there's shielding. So more energy would be required for lithium. Which has the larger second ionization energy? All right. So let's do this one. That's good. What are our choices? Lithium and beryllium. Lithium and beryllium. So lithium is going to be 1s1. Let's see. Lithium is 3, beryllium is 4. So 1s1, 1s2, excuse me, 2s1, correct? And beryllium would be 1s2, 2s2. So the first ionization energies will be a little higher for beryllium, right? Because it's to the right of lithium. And it goes lithium, beryllium. The second ionization energy, this is the first ionization energy would remove that electron and make this a positive. The second one would remove that electron and make this a positive. Now, the second ionization energy, which one? The second ionization energy would get down into the core of lithium. But the second ionization for beryllium would still be in the valence. So this one would be second ionization energy higher value than beryllium. Okay? And this chart shows you that trend, right? The core electrons, you have to remove more electrons as you increase the atomic number. Then you got to remove more of them, more of those valence electrons before you get down into the core. But once you do, the core jumps way up. All right, electron affinity. The temptation, I better leave that there. The temptation for electron affinity, understanding electron affinity, is to think in terms of it's just the opposite of electron ionization, but it's not. Because what we're doing now, instead of removing an electron, we're adding an electron to the neutral atom. So we're starting with the gas again. We have to start with the gas, right? Because we can't let phase changes interfere with our energy calculations, our energy measurements. So we need to add an electron to this one. And what do we get? Well, we get a negatively charged gas, right? Okay. So when an electron comes from infinity down to the atom, what happens? It gives up energy, right? That's going to be a negative value because it's leading the atom. Okay? So the stronger the affinity of this neutral atom to that electron, the more negative that value is. So more negative means stronger affinity. Okay. Now, how about left to right? As we go across a period from left to right, the affinities become more negative. So let's see. Electron affinity, EA, actually increases from left to right. Well, actually, the value decreases. Decrease. What we're saying is more negative. But it's a stronger attraction, which means the value is more negative. Okay. And from, let's see, more negative, general. Down a group, it becomes more positive. More positive, which means less attraction. So EA down increases. Becomes a more positive value. Okay. So the trend from lower left to upper right is more negative. Right? Or an increasing affinity, which is measured as more negative value. All right. Now atomic radius. Atomic radius is not as easily defined as ionization energy or electron affinity. Atomic radius, we have to use several different types of techniques depending on the nature of the element. Typically, if we know the distance between the nuclei of two atoms of the same element, right, if we can measure that distance between those two, then we can just take half the value, right? And that gives us the atomic radius. Here we go. The problem is, right, what do you consider the outer limit of the atom? Right? Sometimes when they come together, they sort of squash a little closer, and that kind of skews the value. So atomic radius, the values that you may see reported in literature or in reference manuals are going to vary within a narrow range. but it depends on how they were determined as to whether they, how closely they agree. Basically, two types of radii are accepted. One is metallic radius. When you have a metal in a crystal structure, then sometimes it's reasonably easy to measure the spacing of in the structure with X-ray diffraction, usually. And that distance between two adjacent atoms then can be determined, and you can calculate the metallic radius. The covalent radius is usually determined as one has the distance between nuclei in a homonuclear diatomic molecule, such as hydrogen, right, or oxygen, or nitrogen. Those would be easy to get at. Others, covalence would be a little more troublesome, right, because not all nonmetals, which is where you're looking at covalence, and not all nonmetals form diatomic elements. Right? Some of them prefer 4. So you would have to force them into a diatomic situation in order to make that measurement. Or sulfur. Sulfur prefers that at room temperature and pressure. And so again, you'd have to separate it. You'd have to devise a way to reduce it to the diatomic. And you can use various methods: X-rays, electron crystallography, neutron diffraction, microwave spectroscopy, and others. Right. So depending on the method you're using, you may get a different answer than some other laboratory. And usually when these values are reported, you're told in the descriptions actually how how it was determined, right? Was it a single determination using this method, or was it a composite? Is one of the problems. Okay, what are the trends then? Well, the trends vary, but if we're thinking of only the representative elements, right, the s orbitals filling and the p orbitals filling, it tends to behave fairly well. It's when you get into the transition elements that things kind of go up and down. But generally speaking, the atomic radius going across a period from left to right, the radius decreases. And the reason for that is you're putting protons and electrons together, increasingly from left to right. But the electrons are going in at the same energy level, so there's not much shielding. You're increasing the effective nuclear charge. So as you increase the nuclear charge, it tends to draw those electrons closer to it. So we're shrinking the atom as we go from left to right. Okay. As you go down a group, you tend to increase the atomic radius simply because the electrons are going into larger and larger orbital sizes, right? I mean, N refers to the energy and the size. So as you go down a group, you're adding electrons to a bigger size, and that makes the atom bigger. All right. Here's a representation of only the representative elements. Right, so you'll notice that lithium, beryllium, well, we don't have to skip anything for those. We don't skip for that one. Potassium, calcium, yes. We do have to skip the transition elements in here. So by the time you get to this other side, they're already shrunk, right, way down. And notice that down, the s orbitals behave themselves pretty well. The p orbitals, they tend to behave reasonably well, increasing in size as you go down. All right. Which should be the larger atom, sodium or chlorine? Well, they're in the same period. Chlorine is further to the right, so it should be the smaller one. Sodium should be the larger one. Lithium and cesium. Right? Lithium and cesium are in the same group. Cesium is way down here. Lithium is way up here. So cesium should be the larger one. All right. Now, let's think about the orbitals themselves. let's compare the 1s orbital for hydrogen and the 1s orbital for lithium. Just think about those orbitals. We know that lithium is 3. So lithium is going to be 1s2, 2s1. And this one's going to be only 1. But let's think about just these orbitals right here. Right? What size is the orbital going to be for this one versus that? Well, look at it this way. We've got 1 proton here. We've got 3 protons here. And we're adding electrons into this same orbit. So what we've got is a stronger nuclear charge drawing this 1s closer to it. So the larger orbital should be the hydrogen, 1s. Okay, we're not talking about the whole atom. We're just talking about that orbital. Once we start adding these out here, of course, it's going to be bigger because we're adding, to a larger space. How about which is the lower energy? Remember, energy is lowest the closer you get to the nucleus. So if the lithium is shrunk down smaller, then the 1s orbitals for lithium are going to be lower energy. They're smaller orbitals, but that makes them closer to the nucleus. So they're going to be lower energy. See, is that all for that slide? Yeah. All right. So let's arrange these elements, oxygen, fluorine, and sulfur, according to increasing ionization energy. So we got oxygen, fluorine, fluorine, and sulfur. All right, let's put them in relative position. Oxygen's here, fluorine's right next to it, and sulfur's below. That's easier to deal with ionization energy. So ionization energy is going to be increasing from left to right and from bottom to top. So if we're putting them in increasing order, the ionization energy should be, first ionization energy should be sulfur to oxygen to fluorine. All right. How about atomic size? Well, sulfur is going to be biggest. Right? Oops. Sulfur is going to be biggest. Right? And then fluorine is going to be smallest. And oxygen's in the middle. So it should go the opposite direction, fluorine, oxygen, sulfur. All right? Okay. Final thoughts on the periodic table. Let me see. Do I need to even talk about that? Okay. The number and type of valence electrons that primarily determine the atom's chemistry. That's why the groups, every member of the group has the same type of valence electrons and the same number of valence electrons. The electron configurations can be determined from the way the periodic table is organized. Right? We know that, and we're going to see some examples in your review questions. And when we talk about them, we can take Thursday and next Tuesday to do review. So come back on Thursday and we'll start the review, and we can take all the time we need. 3, certain groups in the periodic table have special names. Well, yeah, we know about that. Basic division of the elements in the periodic table is in metals and nonmetals. Yep, we know about that too. What's the difference between metal and nonmetal? Right. Qualitatively, metals conduct heat, conduct electricity very well. They have a luster if they're polished. Right? They're all but one of them is solid. Right? Mercury is the only liquid at room temperature. Whereas nonmetals can be any phase, solid, liquid, or gas. They generally don't conduct electricity or heat very well. And let's Let's see, there's a third one. When they're solid, they have very dull appearance. Okay. And that's it.